Hi, this is Anag, and in this video, I'll be proving that the area of a circle is pi r squared. And the area of a circle is a common formula in your geometry class probably. So I hope that you enjoy this proof. Also, a bit of a disclaimer: this proof requires integration. So if you don't know what integration is or how integration works, I suggest that you brush up on that before watching this video. So, how do we prove that the area of a circle is pi r squared? Well, I find that the easiest way to do it is to first find the area of this upper semicircle that I've shaded in blue, and then since the circle is symmetrical, we can then double that area to find the area of the whole circle. So, how do we find the area of this semicircle? Well, to do this, we are going to use a definite integral. And the first thing we need is an equation for this circle. And the equation of a circle written, solved for y, is y, sorry, I had an eraser. Y equals the plus or minus square root of r squared minus x squared. So this is the equation of a circle, but we only want the upper semicircle. And for this, we're only going to need the positive values, which means that for this upper semicircle, the equation is going to be y equals r squared minus x squared, like that. Now, as you may have realized by now, that area shaded in blue is the area under the curve, and that curve being this function. And for that, and to find that, we're going to have to use a definite integral, which means that the area of the semicircle is equal to the definite integral from negative r to positive r. Those are the bounds because we're going from negative r to positive r. And the function that we're going to integrate is the equation for the semicircle, which is r squared minus x squared, the square root of that, and we're integrating with respect to dx. So this is the expression that we need to find the value of. So at first glance, it is not clear how we would evaluate this integral, but one thing that we can try is to do a substitution. And to illustrate what I mean by that, I'm going to use this right triangle. So if I look at this right triangle, and let's call the hypotenuse r. If I call the hypotenuse r, and then let's call this leg x. So if this is r and this is x, by the Pythagorean theorem, it is safe to say that this leg over here is the square root of r squared minus x squared. And then let's call this angle theta. So now, let's say if I took cosine of theta. If I have cosine of theta is adjacent over hypotenuse, which is the square root of r squared minus x squared all over r. So if I solve for r squared, the square root of r squared minus x squared, like this, the square root of r squared minus x squared is equal to r cosine of theta. Now, let's say if I took sine theta. Sine theta is equal to opposite over hypotenuse, which is x over r, meaning that x is equal to r sine theta. So now, what this means is that we can actually rewrite our integral expression, because the square root of r squared minus x squared, that is just equal to r cosine of theta. And then we can use this expression over here, x equals r sine theta, to find what dx is. In fact, let's do that right now. If I know x equals r sine theta, that means that the derivative of x with respect to theta is equal to r cosine theta, meaning that dx is equal to r cosine theta d theta, meaning that I can rewrite my integral expression as the area of the semicircle is equal to the integral, and we need to change the bounds, so let's just leave that for a little bit later. So the integral of the square root of r squared minus x squared, but the square root of r squared minus x squared is just r cosine theta. R cosine theta, and then dx is r cosine theta d theta. R cosine theta d theta. And now we have a new integral expression that is much easier to evaluate. So here I have just rewritten the integral of r cosine theta times r cosine theta d theta as r squared cosine squared theta d theta. And now we also need to know what our bounds are. Initially, our bounds were negative r to r, but since we used the substitution, we have to change our bounds. Since our substitution was x equals r sine theta, we can solve for theta, making theta equal to the inverse sine of x over r. Using this fact, we can find our low bound and high bound, which comes out to be negative pi over 2 and pi over 2, which means that our integral becomes the area of our semicircle equals the integral from negative pi over 2 to pi over 2 of r squared cosine squared theta d theta. Alright, so here is our integral, but how do we evaluate it? At first, it may not be clear, but there is a very useful identity that we can use. Cosine squared theta is equal to 1 plus cosine of 2 theta divided by 2. So let's use this identity. The first thing I'm going to do is that I'm going to pull the r squared out, because r is just a constant. R is just the radius of a circle. That doesn't change. So r squared multiplied by the integral from negative pi over 2 to pi over 2. Cosine squared theta is 1 plus cosine 2 theta over 2 d theta. Now we can pull a 1/2 out. So let's do that. This is equal to 1/2 r squared times the integral from negative pi over 2 to pi over 2 of 1 plus cosine 2 theta d theta. Now let's integrate. So 1/2 r squared, and now we're going to use the fundamental theorem of calculus. If we find the antiderivative of this expression over here, and then evaluate it from the low bound to the high bound, and subtract those two values, we get a value for the definite integral. So let's do that. 1/2 r squared times, now we got to find the antiderivative of 1 plus cosine 2 theta. The antiderivative of 1 is just theta, and the antiderivative of cosine 2 theta is 1/2 times the sine of 2 theta. And then we need to evaluate this from negative pi over 2 to pi over 2, like that. Now let's start plugging in the values. So this is equal to 1/2 r squared times pi over 2 plus 1/2 sine times 2 times pi over 2. You got a sign of pi in there, and the sign of pi is just 0, so that goes away. Now let's do the same for negative pi over 2. So hold on, let me just erase this plus. That should not be there. So if you do the same for negative pi over 2, we have a minus negative pi over 2 plus 1/2 sine times 2 times negative pi over 2. We have a sign of negative pi in there, which is also 0. So we have this, which is equal to 1/2 r squared times pi over 2 minus negative pi over 2 is the same as pi over 2 plus pi over 2, which is equal to pi, meaning that the area of our semicircle is equal to pi over 2 r squared. But this is the area of our semicircle. The area of our total circle is equal to 2 multiplied by the area of the semicircle, which is 2 multiplied by pi over 2 r squared, which is equal to pi r squared. Therefore, we have just proved that the area of a circle is pi r squared. Thank you for watching this video, and if you want more content like this, please be sure to subscribe. Also drop a like to make me feel better. Thank you.